All right, so we're going to look at this central limit theorem, which has to be one of the most crazy results from statistics. And in order to do that, we need to understand a little bit about the distribution of the sample mean. Now, I'll be honest, 3 Blue 1 Brown is an amazing YouTube channel, and they have explained the central limit theorem very well there, so I'll put a link to that below. This video, I think, can add some value just in terms of aligning it with the Victorian curriculum and sort of showing you some of the mathematics you might need to do by hand on assessments and those types of things. But let's have a look at the distribution of the sample mean. So basically, I don't like the term sample mean. I think it, in my mind, the distribution of the mean of the samples. So you've got some population, you want to take the average of these samples that you collect. So if we start doing that, we're going to have a running problem throughout this, and it's going to be about this. We don't know this distribution, but we're going to say that some warehouse ships online orders. The average delivery time is 8 days, with a standard deviation of 4 days. So on average, they deliver it in 8 days. The sort of average spread is 4 days, and we randomly sample 64 orders and calculate their mean delivery time. What is the probability that the sample mean, or the mean of that sample, is less than 7.5 days? Now, what I just want to point out here is that we don't know what the distribution is. And what's going to be such an interesting conclusion of the central limit theorem is that it actually doesn't matter. So maybe I've given the game away a little bit, but keep that in mind as we go through. So to know this, to answer this kind of question, we would need to know the distribution of the sample means. So in order to know the probability that the sample mean is less than 7.5 days, we would need to gather some information. Maybe we could do lots of samples and then work out where 7.5 days sits in that sample, and then work out the probability that it's less than that, right? So let's have a look at another example that'll hopefully bring us all together here. And when we have normal populations, right? So a classically normal distribution is heights. In this example, we've got women's heights. And so suppose we have a normally distributed random variable x that has a mean of mu here, and that sigma squared is the variance squared. So remember, the variance is a measure of spread. If we take the square root of the variance, we get the standard deviation. And then we know that x is exactly normal. So it has this nice normal bell shape for any sample size n. So for women, we know, I'm not sure how accurate this is, but the average is 165 centimeters and the variance is 36. So we have a standard deviation of 6 centimeters. And if we take random samples of size n, here is our population in blue. So we can see it's quite spread out. But this is the heart of the whole thing, right? If you took samples of size n, and we spoke about this in the previous video, but the distribution gets narrower. And one way to think about it is, if you've got your whole population and you start selecting people in a sample, the average, the distribution of the averages is going to be much narrower, because in any one sample, the tall people are cancelling out with the small people and moving us closer to the average, right? So our variance shrinks. So it says here it's narrower, and this is exactly how it's narrower. The standard deviation becomes whatever the original standard deviation is divided by the square root of n, where n is the sample size. In this example, we're taking sample sizes of n. So we have 6 divided by the square root of 9, which is 6 over 3, which is 2. So we can see that it gets significantly narrower when we look at the distribution of the means of the samples, right? And yeah, so in this yellow box, we have the result for a normal population. If we have, a normally distributed random variable with a mean of mu and a variance sigma squared there, then the x bar, the distribution of the sample mean, or the mean of the samples, is normally distributed with the same center. That should make sense. The average stays the same, but the variation is now divided by n. And you can see how that's a consequence of rearranging this formula down here. But essentially, this is what our sort of takeaway information is. We divide the variation by the size of the sample that we took. Okay, so that's when our population is normal. So maybe that's what we expect. Where this video sort of gets a bit more interesting is when we have what's called skewed distributions. So what if the population is not normal? So many real populations are skewed or otherwise non-normal. So wait time. Let's do an example at a cafe. I'll just wait until all this loads. But if we think about an example at a cafe, the wait time X is right skewed. So most people wait under 3 minutes, but occasionally have long wait times if it's particularly busy, right? So in this situation, it's clearly not normal in the blue curve here, but we've got an average of 3 minutes and a standard deviation of 3 minutes. Again, what is so interesting here is when we take a sampling distribution of the averages for different sample sizes. So we've got, we take sample sizes of size 5, samples of size 30, and samples of size 100. We can see as n grows, the distributions become more normal and they become less spread. Now, isn't that interesting? Something that these wait times are completely right skewed. They've got a big skew off to the right, but the distribution of the averages becomes normal. And the larger the samples you take, the more narrow it gets and the more normal it gets. And that's essentially what the central limit theorem says. Just take a moment to sort of digest that, because I think it's a fascinating result. I'm just trying to, maybe I'll pause and maybe I'll just add this. And it's just the point that if you're taking lots of samples, you're minimizing the effect of outliers. And so in all of these samples that we've taken, we're going to end up, if you take large enough samples, your values for those samples go close to the mean. And so you end up with these distributions that are normal. And that's essentially, as I said, what the central limit theorem says. So let's bring it all back together a little bit here and look at a bit of a simulation. Okay, so here's our cafe population. We've done 80 samples of size 5, 80 samples of size 30, and 80 samples of size n. And the code behind this has literally just taken the simulated values for a right skewed distribution with a mean of 30 and a standard deviation, mean of 3 and a standard deviation of 3. We can see that for when we took 80 samples of size 5, that it was quite wide. The spread was larger, and we should expect that because the effect of outliers in those samples is not washed out as much. But then when you're taking samples of size 30, you can see that it gets narrower because, again, those outlier values, when you take the average of that sample, because remember there's 80 different averages in here, it gets narrower. And then when you take samples of size 100, it gets very narrow, and it gets and it's very normal. Okay, so yeah, I think that's a fascinating result. Yeah, and then so that's what you get. I think hopefully it's starting to make a little bit of sense. The sorts of problems we can tackle with this, and this is the crux of it. So this is what's called the central limit theorem. Okay, so let x be any random variable with a mean and standard deviation. It can be any, doesn't have to be normally distributed. And for a random sample of size n, as long as it's large enough, the sample mean is approximately what we said it was before. And the expected value, or the mean, is just mu. So I should be clear about this. For a sample mean that's normally distributed, which it will be because of the central limit theorem, you have that it has an average of mu and a variation of this, a variance of this, which is sigma squared on n. And this is basically just saying the expected value is mu and the standard deviation is that. And so, these are the consequences. Your distribution of your sample means, or the mean of your samples, is centered on the population mean. The spread of x shrinks as n increases. As we said, you divide by the square root of n to find out how much that standard deviation decreases. And the shape of the distribution of the means of the samples approaches normal regardless of the population shape, which we showed with the cafe. Even in the cafe situation, we ended where we had heavily skewed data. we end up in a situation where the distribution of the averages of the samples is normal. All right, so let's now look at how to apply that to our running problem that we've been looking at. So here it is again. So essentially our problem from the start said you've got some distribution, you don't know what that distribution is, but you know that it has a mean of 8 days and a standard deviation of 4 days. And now we're taking a sample of size 64. And we need to find the probability that the distribution of the mean, we need to find the probability that the mean of that sample is less than 7.5 days. But, you know, if we just think about that for a second, how can we know that? In order to know that about this sample of 64, whether it's the average of that is less than 7.5 days, we need to know about the distribution of the sample means. So this is where we need to invoke the central limit theorem, and we need to apply the central limit theorem to this, because we need to understand what do the averages look like. And what we just spoke about is that the averages are normal. And so if we apply the central limit theorem, our first step is to do that. We've got a big enough sample, okay? That's the first thing to note. 64 is big enough. It's larger than 30, so that's more than enough to be able to say that we can apply the central limit theorem. And we can say that, all right, the distribution of the sample, the distribution of the means of the samples will still have an average of 8, which should make perfect sense, but the variation has been shrunk. It's been made narrower. And it's been made narrower in this way. If you're unsure where I got this, just flick back to the previous sort of section. But basically, you take the standard deviation squared, so you get 4 squared on 64. So we can say that the mean is 8 and the variance is 0.25, so significantly smaller. 4 squared, 16 divided by 64 is 1/4. So we've applied the central limit theorem to understand what our distribution of the means of the samples looks like. And now we need to find the standard deviation. Okay, so the standard deviation is sigma over the square root of n for the mean for x bar, which is the distribution of the sample mean. Again, that was on a previous slide there. So we get 4 divided by the square root of 64, which is 0.5. Okay. And now this next part is the part that can be a little bit tricky and we haven't really spoken about, but it's what's called this standardization process. So let me just explain that for a second. So the standard normal distribution has a mean of 0 and a standard deviation of 1. And sometimes when we know we've got normal data, which we do here because we know that the central limit theorem applied to any population distribution will give us a normal distribution, we can use this standardization process to basically transform our distribution into a standard distribution and then use that to calculate probabilities. So just keep that in mind. The standard normal distribution has a mean of 0 and a standard deviation of 1. So you've got, -1 and +1 to the right of it. And this is the standardization process. You basically take your value, which in our case is 7.5. You take away the average and then you divide by the standard deviation. We'll talk more about this in another video. But basically that's called the standardization process. I think a picture here will help. So I'm just going to let this play. And so in blue here, we have the distribution of the sample mean. And that distribution of the sample mean, we can see, is quite narrow. It has a mean of 8, so 8's right in the middle, and a standard deviation, a spread of 0.5 squared. And so we end up with a situation where after this standardization process, saying that x bar, the distribution of the sample mean, is less than 7.5 is saying the same thing as the standard normal distribution being less than -1. So being less than 1 standard deviation below the mean, which you can calculate has a probability of 0.1587. I'll put a link to a picture explaining the probabilities to be below 1 standard deviation and above 1 standard deviation. But that value there should check out. Essentially, you've just taken a problem and you've sort of compared it to the standard normal distribution. So to say that this situation has a mean less than 7.5 is the same as saying the standard normal distribution has a value less than -1, which turns out to be about 15 or 16%. Okay, so hopefully that's interesting and making a little bit of sense. Let's look at the very last part, which is a summary. So here it all is. There's the standardization formula you can have a look at as well if you like. But basically all this is doing is saying if you've got a population that's normally distributed in this first row here, then any n, the sample size of any n, will give you a distribution of the means of those samples to be exactly to have the same mean, but then the variance will be you divide by n. The variance gets narrower. Okay, if it has any shape, so it's not like heavily skewed, but it's got some other sort of distribution to it, as long as you take a sample larger than 30, then you're going to be fine. The central limit theorem will kick in and you'll end up with a normal distribution like we saw with the cafe. We saw with the cafe, like n equals 5, you know, it wasn't perfect. It was actually still had a bit of skew to it. But then by the time we did 30 samples, we did 80 samples of size 30, then, you know, we were getting a normal, approximately normal distribution. And even if you've got heavily skewed data, if you have n, the sample size that you take, to be greater than 50, then you're in safe territory. It's approximately normal. So isn't that interesting? These are some key formulas. Let's just maybe finish up with this. So the CLT is always, the central limit theorem is why the normal distribution appears so frequently in statistics. Averages of large samples are always approximately normal. So I think it's an amazing conclusion. You can have, you know, this data that's, you know, very heavily skewed, and then the central limit theorem kicks in when you find the averages of the samples. And so you can make some awesome conclusions, I think, about populations where it would obviously be impractical to survey or to gather data about every single object in that population. So hopefully that made a little bit of sense. If it did, give us a thumbs up. Hopefully all your studies are going well. If you want this code and you just don't want to hear me bang on, I'm going to just send you the code and you can just play it out. I think it all looks pretty good. I might talk in another video more about the standard normal distribution because that was probably a tricky part to this. In any case, good luck and I'll see you soon.